Good morning, student. Welcome to Urban Pro. In this session, I am going to discuss about Bohr's model and spectrum. This is all about a hydrogen atom. So Bohr's model is actually applicable for hydrogen atom, also for lighter atoms, in which a single electron revolves around a stationary nucleus. Okay. And when electron jumps from one stable state to another stable state, we get to see light. Light is emitting from the hydrogen atom. Some of the radiations is visible, that is light, and some of them is not visible. And we get to see spectrum from hydrogen atom. We'll discuss on this thing. Okay. So initially Bohr's atom, what is that actually? Bohr's atom. Initially, people Bohr's atomic model. So initially, people had no precise idea on atom, where the nucleus is situated, how the electron is revolving, how the orbit of nuclear electron, is this a circle, is this an elliptic? Okay, so people had no precise idea on atom. By that time, Bohr came with his model, and we are going to discuss about that model. Okay, so that is known as Bohr's atomic model. So Bohr's actually postulated his model, postulated the atomic model, and in his model there are three postulates. So first we will learn about those postulates. Okay, so the first postulate is all about the path of the electron. Okay, listen carefully. In mechanics, we know that whenever a particle is moving round a circle, even if the speed is constant, then also there is a acceleration of the particle. The reason is the velocity vector is changing, although the speed is constant, but still its direction is changing continuously. So ultimately velocity is changing, so there is some acceleration for constant speed, still the acceleration is there, and we call the acceleration as centripetal acceleration, isn't it? And from electromagnetic theory, we know that whenever a charged particle is accelerated, it emits electromagnetic radiation, isn't it? So a accelerated charged particle emit electromagnetic radiation. That is, it emits energy. So there will be some loss in energy. When the energy is lost of a electron, so ultimately it is obvious that it will be revolving and its radius will be decreasing. Ultimately it will fall on the nucleus, but it is not the case, it is not the real scenario. So how the model is? So the Bohr's postulate was, the first postulate was that yes, electron can move, electron can revolve around nucleus in certain circular stable orbit. We say the Bohr say circular stable orbit without emitting electromagnetic radiation. Okay, so this is the one of the postulate of the Bohr's model. Okay, the second one is about, it is revolving round a circle, it's fine, but in which circle? Not in all circular orbit. There are certain stable circular orbit, and the radius of the circular orbit, I mean the circular orbit will be such that its angular momentum P will be equals to the n times h by 2 pi. If we write it in words, the circular, okay, the electron can revolve, the electron can revolve only in those orbit in which the angular momentum of the electron in which the angular momentum of electron is integral multiple of h by 2 pi, where this h is Planck constant. Okay. Now, mathematically, the angular momentum P is equals to nh by 2 pi. This P, that is angular momentum, we can write this as mvr. When where r is the speed, where r is the radius of the circular orbit, v is the speed with which the electron is revolving, m is the mass of the electron. That has to be n times h by 2 pi. And what is n? N is, as here it is written, that it is the integral multiple of h by 2 pi. That is, the value of n is 1 2 3 4 dot dot dot. Okay, so here mvr by h, mvr is equals to n times h by 2 pi. This is the second postulate. Okay, but yes, as we know that we get to see the spectrum of hydrogen atom, so definitely those electrons emit electromagnetic radiation. But when they will emit this electromagnetic radiation? When a electron is revolving around a round nucleus on a circular path or orbit, it is not emitting any electromagnetic radiation. Then when it emits electromagnetic radiation, this says from Bohr postulate is that when electron can jump, Bohr is saying electron can jump from one stable orbit suppose the energy of that stable orbit is E1. So from one stable orbit to another stable orbit, suppose the energy is E2, the energy of electron is E1 and E2 in when the electron is revolving on these stable orbits. Okay, so electron can jump from one stable orbit to another stable orbit with absorbing or emitting electromagnetic radiation of frequency f such that the energy difference E2 minus E1, E2 difference E1, or we can write E1 difference E2 equals to HF. Okay, so let me repeat this. Suppose this is the nucleus and this is the first orbit, this is the second orbit, this is the third orbit. So suppose an electron is revolving on third orbit. Now it jump to the first orbit, so this is the jump. Okay, so n is equals to 3 to n is equals to 1. It jumped from n is equals to 3 to n is equals to 1. Then one electromagnetic radiation will emit. Okay, similarly, suppose an electron jump from this n is equals to 2 to n is equals to 3 this way. Okay, then it will be happen only when an electromagnetic radiation will be absorbed. This an electron will absorb an electromagnetic radiation, then only it is possible to jump from a lower orbit to higher orbit. Okay, so here absorption is taking place and here emission is taking place. Okay, so whenever electron can jump from one stable orbit to another stable orbit by absorbing or emitting electromagnetic radiation. Okay, and the relation is E2 minus E1 is equals to HF. So let us recap once again these three postulates. Electron can revolve around the nucleus in certain circular stable orbit only and without emitting electromagnetic radiation. And the second postulate, it says about the electron can revolve only on those circles in which its angular momentum is multiple of h by 2 pi. And the third postulate is all about the electron can jump from one stable orbit to another by absorbing or emitting electromagnetic radiation. So electron emits electromagnetic radiation or light, some extent of light, when it jumps from a higher orbit to lower orbit, and in such a way that the frequency of the light will be such that it will be just the if the frequency is f, then hf, that is the energy of the photons of the wave or radiation, will be equals to the difference of energy of the two orbits between which the jumping is taking place. Okay, so these are the postulates. Now we will move on to discussion of energy. Definitely we can't derive a lot, but still we will precisely we will discuss a little. See, from the postulate 1, we can say that the electron revolves in a circular orbit. As we know from mechanics that whenever a particle of mass m, speed v, revolves around a circular orbit of radius r, it needs centripetal force, and the magnitude of the centripetal force is mv square by r. Who will supply this? In this case, the electrostatic force between the nucleus and the electron is the responsible for this centripetal force requirement of mv square by r. So that is nothing but 1 by 4 pi epsilon naught, as you know, q1 q2 by r square. Here we will write Ze, that is the charge of the nucleus, and the charge of the electron by r square. Let's say this is equation 1. Okay, the another equation we can write, nothing but the mathematical form of the second postulate, that is mv square by mvr is equals to n times h by 2 pi. So from these two equations, by solving these two equations 1 and 2, we can get the value of speed with which the electron is revolving. Once we know the speed of the electron, we can easily write the expression for kinetic energy of the electron, which is nothing but half mv square. So in our expression half m, there will be some complicated form of velocity, and we will take the square of that. Then we will have the kinetic energy. Okay, so definitely I am not going to write the full and final expression for kinetic energy, but let us discuss further. Okay, now we will discuss potential energy. What will be the potential energy? Using the potential energy formula from the electrostatic potential chapter, potential energy was what? It was nothing but 1 by 4 pi epsilon naught q1 q2 by r. So here q1 is Ze, as you know, and minus E is the charge of electron by R. But you may confuse with the charge that the way I have written here. Here I have written ZE, that is the charge of the nucleus, positive charge, fine. But here E, but here minus E. Why this? The reason is we are equating these two forces. We are taking the magnitude of the force only, isn't it? And here, as the potential energy, it is the magnitude. The negative sign is important here. Okay, so suppose this is equation, another equation, equation 4. So from this equation 3 and 4, that is the expression of kinetic energy and potential energy, we can easily get the expression for total energy of the electron, which is nothing but minus RCH Z square by N square, where Z is the atomic number, N is the number of the orbit in which the electron is revolving, and TE is the total energy of the electron revolving in the nth orbit. Okay, so we write it as En, that is the energy of the electron revolving in nth orbit. Okay, for hydrogen it is minus 13.6 by N square electron volt for hydrogen atom. Okay, we will discuss on hydrogen atom. So this is a very important formula for us. Now as we will move on to spectrum. So Bohr's model is all about this, and now we will move on to spectrum. What is spectrum actually? Spectrum is, as I just told, that we need this formula. Okay, spectrum, hydrogen spectrum, better to say. We will discuss hydrogen spectrum. Okay, so this is hydrogen spectrum. What is hydrogen spectrum? See, suppose you take a cylinder, and here somehow here hydrogen atoms are there, lots of hydrogen gas is inside this cylinder, and some high potential is applied. Okay, what will happen? Current will flow through this, the electrons will be excited, they will, suppose this is the nucleus, this is the orbits of the atoms. Okay, so electron revolves in ground state in n is equals to 1. By taking energy from this current, they will be excited to the higher orbits like 2, 3, 4. They will move up to the higher orbits, and after few, not few seconds, only few microseconds only, they come back to the lower states by emitting electromagnetic radiation. Those electromagnetic radiations are usually in, basically these are the spectra. These electromagnetic radiations are of different frequency, wavelength, and there are some series of wavelength. We'll discuss on that. Okay, so hydrogen spectrum, what happens? Initially I'll draw the nucleus. What is this? This is nucleus, and I'll draw some orbits of the hydrogen atom. Suppose this is n is equals to 1, then I am drawing n is equals to 2. Let me how to keep it. Okay, n is equals to 2. This is n is equals to 3. Okay, so this is n is equals to 1, this is n is equal to 2, this is orbit number 3. Fine. When the electron is n is equals to 1, it will revolve. Fine. Now, suppose electron is revolving is n is equals to 2. The electron can jump from n is equals to 2 to n is equals to 1. Okay, so when the initial number of orbit is 2 and the final is 1, or I can write in other way, suppose the final orbit is 1 and the initial orbit is 2 or 3 or 4 or 5 dot dot dot. That is, the jumping is from n is equal to 2 to 1. It may be 3 to 1. It may be from some other higher orbit like 4 to 1. So whatever be the initial state, uh, if the final state is 1, that is final orbit is 1, then see the electromagnetic radiations will come up due to all the transition, isn't it? All the transitions, electromagnetic radiation will come, and these radiations are known as Lyman series. These are known as Lyman series. To be very precise, we'll write how. In his first, we'll discuss Lyman or Lyman series. So series, this is series of some wavelengths when electron jumps. The final state is n is equal to 2. Initial is greater than 2, that is 3, that is 1. That is 1, and the initial orbits may be higher, greater than 1, that is 2, 3, 4, and so on. Then the wavelengths are known as are of Lyman series. Okay. So what will be the wavelength in this case? Let us discuss it here. See, as we know from our first discussion, E was nothing but minus 13.6 by n square, isn't it? Okay, we can move on to here as well. Let us take this equation. Let us take this equation. That is the total energy. Let us discuss this equation. The total energy is what? The total energy is what? Total energy is this, isn't it? See, energy E is equals to minus RCH by Z square by N square. Fine. E is equals to HC by lambda minus RCH Z square by N square. So from this, CH will be cancelled out from the both side, and we will left with 1 by lambda is equals to minus Z square by N square, isn't it? No. Actually, this is not energy only. This is difference of energy. This is difference of energy, as you know. E2 difference E1, isn't it? E2 difference E1. So here we will have actually E2 minus E1. So n final square by 1 by n initial square. Let us take the Z square here. So what we will have, let me erase this one. So 1 by lambda will be what? Finally 1 by lambda will be minus r times 1 by final square minus 1 by initial square. So now we'll just put the what is the initial orbit, what is the final orbit. Putting this, we'll get the lambda, that is the wavelength of the radiation. Okay, so Lyman series is defined that way. When the final state is n is equals to 1, the final orbit is 1. Whatever be the initial orbit, definitely the initial orbit has to be greater than 1, that is second, third, fourth, and so on. The next series is Bohr series. In this series, there are only few lines or wavelength which we can see. The series from Lyman series, the wavelength are not visible. Only few wavelengths from Bohr series can be visible. What is the definition of the, what are the wavelengths which is under the Bohr series? In this case, when the final orbit is 2 and the initial orbit is greater than 2, that is 3, 4, 5, 6, and so on. If we want to draw schematically, suppose this is nucleus, this is suppose orbit 1, this is orbit 2, this is orbit 3, this is orbit 4, and so on. So the final state will be 2. So this one, when electron jumps from the state 2 to 3 to 2, this is Balmer series. Okay, this is under Balmer series. Let us draw few more orbit. Let us draw few more orbit. Okay, these are the higher orbits. Now suppose electron is jumping from n is equals to 4 to 2. So the jumping is like this only. Okay, suppose it is jumping from the higher orbit to 2, suppose here to here, this is also so these are the jumping corresponding to n is equals to 3, 4, n is equal to 5, 6, 7. Okay, so wavelength will be, I mean radiation will be emitted corresponding to all of them. For this, a wavelength will be emitted. For this jumping, a wavelength will be emitted. From this, a wavelength will be emitted. For this, wavelength will be emitted. For this, a radiation will be emitted. So these are what the radiation of Balmer series. Okay, I hope the concept is clear. Now the next series is Lyman-Balmer Paschen, P-A-S-C-H-E-N, Paschen series. Okay, for Paschen series, it is the final state is the final orbit will be increased by one, that is 3, and the initial is what, greater than 3, that is 4, 5, 6, and so on. Definitely we will not draw again. So Lyman, Balmer, Paschen, bracket. Okay, in bracket series, here the final state is definitely it will be increased by 1, that is 4, and the initial ones are 5, 6, 7, 8, and so on. Okay, the next series is fund. Okay, I hope you now you can get it, what will be the initial and final. So the final state will be just increased by 1, that is 5, and the initial one will be 6, 7, 8, 9, 10, and so on. Okay, so these are the spectrum corresponding to hydrogen atom, Lyman, Balmer, Paschen, bracket. The final state is 1 for Lyman, final state is 2 for Balmer, final state or orbit is 3 for Paschen, and final orbit is 4 for bracket, and for fund it is 5, and the initial state is just greater than 1 or more than that. Okay, so this is all about this Bohr's model and spectrum. I hope you all understood it well, but still if you have any doubt, do contact with me through my profile in Urban Pro. Thank you, see you in the next session. Okay.